before in this conference, but I mean with a quite different goal in mind. The lofty goal of this whole project is to obtain a coherent realization of the trace. I'll recall what all of these objects are in a bit. Just want to give the motivation here. So the trace of the affine Hecke category in type A. So this is the motivation of this whole thing, and our contribution is significantly less lofty than this, but I hope it will inform the overall goal. So this is my joint work with Eugene. Right. Okay. Our contribution is to describe what such a hypothetical realization would do to objects. So describe this hypothetical realization on the set of objects. Now, just our opinion is that this definitely exists, but we are very, very relaxed about the word hypothetical here. It's just that we don't have the tools to actually prove that. It gives everything we want from this realization. All right, so let me tell you what these objects are already. Let's start with the homotopy category of AS Biennial. So this is an object which we've seen in this conference. I will just say what it is in words. This is the homotopy category of the tensor category of extended affine sorgal bimodules in type A n minus 1. And, defining this category would be extremely interesting, but it will take up a lot of our time, and I'm sure lots of people in the audience will know the definition. The only thing which I will need for the purpose of this talk is that this includes objects. I mean, since I'm really doing everything on the level of objects, let's just focus on objects. It includes objects T1, Tn minus 1, Y1, Yn, which correspond to the following braids. So I'll draw the braids for you. Now these are affine braids. These are affine braids on n strands, so therefore they will be represented by n strands and a pole, and going around the pole matters. So Ti is this n strand braid with a pole, so the one that everybody knows and loves. This is strand 1, strand I minus 1, strand I, strand N. And Yi, well, let me write the braids with small letters. Yi is going to be this thing. The pole is here. This is strand 1, strand I minus 1, strand I, strand N. Is it wrong? You're
I and I plus 1, not I minus 1.
I think by TI already, yeah, I plus 1, yeah, exactly.
Yeah,
I plus 1. Oh, yeah, that's right. Absolutely. I get the Y wrong, though. I was actually expecting to get the Y wrong and not the T. It's quite a performance. All right. So these are the braids which correspond to them, and then I will write some stacking of these braids for you, and then by this picture, the braid picture of the objects will be completely defined. So I won't tell you what these objects are in terms of orbital high modules. it would involve too much time, but it's super interesting. Instead, I will just show you some products of these capital T's and capital Y's, and then you can easily tell the grades that they correspond to. However, before I do so, I do have one more piece of technical data to introduce. This is the horizontal trace of the category. Because ultimately, I'm not just interested in this category, I'm interested in its trace. So let me introduce a definition, which once again, I'm sure lots of people here know, but just...
When you say objects associated with braids, you mean Rouquet complexes?
Yep.
Oh.
Yeah. I just don't want to tell you what the Rouquet complexes are.
When you say extended, do you mean you allow rotations along the circle or not?
Extended means that it has this his object, which is called omega. I mean, yes.
Around the circle.
Yeah. Okay. So, but I don't want to tell you what omega is because I won't need it.
But
It's like Hawaiian Tn minus 1 to the other T1.
generated by T's and Y's. Extended.
Yeah, so a rotation is like a Hawaiian Tn minus 1 to the other T1, if I recall. But the definition of the horizontal trace. So if C is a tensor category, and once again you can say a bunch of words like DG category and so on, but I won't need them for the purpose of this talk, then its trace, let's see, is the category, which is not a tensor category anymore, but it's a category with the same objects, by different morphism sets. Morphism sets are given by the following rule. So, home in the C from X and Y, I mean these can be thought of as objects in the trace or in the category. The home space is the direct sum. I guess I'm implicitly assuming these categories are additive, but it's not a problem for us. So this is home inside C from Zx, Yz. So what you see here is that you don't just look at homes from X to Y, you allow yourself to multiply it to tensor by anything on the left in the domain and by that thing on the right in the codomain. But then you impose a relation which identifies morphisms in the summand for Z with morphisms in the summand for W, and the specific identification is the following. So whenever you have a composition of this form, which is of the form F tensor ADX, and then you compose it afterwards with a morphism from this to YZ, then this should be identified with the composition WX YZ, and here you have 8y tensor F, and here it goes to YW, and this should be true for all applicable morphisms F and G and all applicable Z and W. So for any object Z and W, for any morphisms F and G, as indicated in this diagram, you identify this composition up here with this composition. So you see that in that way you identify a home from the summand corresponding to Z with a home in the summand corresponding to W. And the reason you could do that is that this ensures that in the trace we have the identity which we like. Fg is equal to Gf for any two composable morphisms. Let's say it like this. F goes this way and G goes this way. I mean, the property over here is stronger. This is a special case of that property, but we use a stronger property because we also want to guarantee that this construction is universal in a certain sense, which I will not expand on. Yes?
Is it possible to draw a picture with equivalence relation because so many of us are visual people?
Yes, but I am not. So the question is that it's not possible. A picture of the top of my head. I mean, we have it in our paper. The top of my head. The most complicated pictures of braids I can draw are these ones.
That's comparable in complexity.
Well, yeah, I know. Okay. Okay. Yeah, some of us are very Okay, so finally, you know, I have a feeling that I bored at least half of the audience, but at least finally I can say what the objects that we want to study, the categories that we want to study in this talk. So in this talk, we will consider the category which I will denote by N, and this is the trace, the homotopy category of affine sortable bimodules for any n. So it's this category whose coherent realization we want to describe. You know, first of all, we want to show that the coherent realization exists. And this category already actually first appeared in Kostya's talk on Monday, right? So people have already seen this kind of thing. Good. So let's construct something explicit. Let's construct some objects in this category. So for any n tuple of integers, and I'm going to write my n tuple of integers in a very, very funny way. So this is dn1 plus 1, dn1 plus n2, dot, 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 dot. So this is inside Zn, where n is n1 plus n2 plus dot, dot, dot. So already such an n tuple of integers, and this is really an n tuple of integers decorated with a composition of the number n. You know, but I'm going to keep this implicit in the notation. Let's define the following object. The object is y1 to the d1, yn to the dn. I should have said, and I completely forgot, that the y's commute. They commute in the category of affine sortable bimodules, so you know, I can multiply them in any way you want. This thing is like very nice and predictable, but let's also multiply this by a bunch of t's. So take the first n1 minus 1 t's, then jump 1 t, and then take the next t n2 minus 1 t's, and just do this for essentially every part of this composition. So the composition is essentially telling you which t's to throw out from the product. So what you have over here is a subword of the Gaussian word. And this now, I will think of this as an object inside N. So an object in the trace of the affine Hecke category. It's definitely an object in the Hecke category itself. But we will study it as an object in the affine Hecke category where it has a lot more morphisms, and well, the morphisms are different. So we construct this object, and the first result I can actually state, this is a lemma is that these objects generate a trace. So generate means that anything in a trace can be obtained as like a successive cone of some kind of complex of these objects. And it's actually not even these objects, but a subset of these objects. And I want to tell you exactly which subset. So N is generated by, let me actually give a name to this thing. It's always ED. And it deserves a box. This also deserves. Yes?
Does that definition, actually maybe I don't.
Is the category triangulated?
Yeah. I mean, there are also DG modules of all of these categories, but yeah, triangulated is good for the purposes of this talk.
The RM is triangulated.
Yes, I mean, the original triangulated structure of the original category says these are non-trivial facts which I'm glossing over for the purpose of exposition. So let me tell you what the trace is generated by. So I said it's generated by a subset of these objects, EDs, and now I want to tell you exactly which subset and what is the combinatorics of these objects. So I will denote the generators by EP, and now I have to tell you what P is. So P runs over convex paths in half of the lattice plane. So a convex path in half of a lattice plane looks like this. So where M1 plus M2, M1 dot M2 dot are integers, n1, n2, is n, and n1 plus n2 plus ... is equal to n. So this runs over convex paths. So, to emphasize the fact that I'm not a very visual person, this is how I visualize a convex path. And it's understandable I can go like this. So let me actually draw a picture here so I can show you how to view this as a convex path. You basically draw your Hadis plane, and associated to these numbers m1, n1, m2, n2, you draw a path starting from the origin, which the length of this vector is n1, or like this vector is n1, m1. Then you follow it up with the vector n2, m2, and then so on and so forth. And the inequality ensures that the slopes of the paths are increasing, i.e. it follows a convex path. And it's a lattice path because these numbers are all integers.
In the definition of e to the d, you have a sequence of integers.
E to the d is more general, so I have to tell you what EP is. So far I've only told you what P is. P is indexed by convex paths. So now I have to tell you exactly what EP is, and EP is a particular case of the EDs. Now, the particular ED which you see here is, I have to give you some explicit integers. And the explicit integers associated to this convex path is given by some kind of integral parts, and the specific integral parts which you put here are these numbers. I minus 1 bar n2 divided by n2 I n2 over n2 I minus 1, and so on. So, the convex path implicitly has the information of n1, n2 which sum up to n, so it implicitly knows about the composition. So if I know the convex path, I know how to put my bars here, and within each consecutive chunk between two bars, I put some integers which only depend on the ratio n1 over n1 in the first one, n2 over n2 in the second one, and so on. And the specific integers, if you've seen the kind of combinatorics that Eugene and I have been working on, and other people in other contexts, then this appears all over the place. And if you haven't seen that, then I'm afraid it'll seem kind of weird. But at least there is a way to take a convex path, which is either this kind of geometric picture or this kind of picture of rational numbers in a certain order, and produce for them an n-tuple of integers. And because you produce an n-tuple of integers, you can produce such an object in the trace as in the orange box. And the statement of the lemma is that these guys generate a trace.
It's I or
I. No, here I goes from 1 to n1, because you need n1 numbers here. Here I goes from n1, from 1 to n2, and so on. Sorry, I didn't want to be too precise about this because these numbers will not really be so important. What is important here is that there is a prescription which takes a convex path and produces an n-tuple of integers, and from that n-tuple of integers you get this kind of object in the trace. And these generate.
And you mean generate as a triangulated
As a
pattern?
triangulated.
Maybe information about source nodes, since people.
Yeah. So yeah, I kind of should have, trying. Getting about the visual aspect of this whole thing. So when the convex path is a single line segment of slope m over n, let's assume that m and n are coprime. In that case, these particular indices here are exactly the indices that we discovered and we studied in relation to torus knots with Eugene many years ago, and which personally got me into this whole business. And in fact, I think it has been known for, 50 years or something, that if you stick those particular integers into these particular powers, then the braid over here closes up to the torus knot. I don't know, 50 is probably an understatement, maybe more like, maybe significantly longer. Yeah, so those numbers indeed, they seem strange algebraically, but topologically, if you draw the corresponding concatenation of braids, then you get the closure of that is the MN torus knot. So what this thing is, I mean, assuming that the mi's and the ni's are co-prime, what this thing is essentially setting side by side. I mean, it's a link whose components are the M1 and 1 torus knot, then the M2 and 2 torus knot, then dot dot dot, and so on and so forth. If Mi and Ni are not co-prime, then it's a bit tricky, but it's some kind of torus knot decorated with some representation. Okay, so this is M1, and it shows that these objects do not generate the affine heavy category, but they do generate its trace. And we have some hopes that one can even get a description of the trace as generators and relations with these things, but so far it's just a vague hope. So much is still to be understood about these guys. All right, so this is half of the picture. I told you what the category is. I told you what the generators is. But now I'd like to say something about the coherent realization. So let me switch gears completely and move on to algebraic geometry. Is there any questions? Okay. So
Could you give some very rough intuition of why these objects should generate? If possible, that's fine.
no, generated as a triangulated category. It's essentially a bunch of skein relations. So skein relations give you triangles in this triangulated category, and they allow you to move arbitrary products of y's and t's and put them in the right order. I mean, essentially, these objects are products of y's and t's in a certain order, and the powers of the y's are certain numbers. So if you have like an arbitrary product of y's and t's and an arbitrary product of y and t's, then use the skein relation to move the y's to the left, the t's to the right, and this only works in the trace. It doesn't work in the original category. Okay, so let me show you the geometric version of this. So once again, for the same kind of D, for the same kind of n tuple of integers, but when I say n tuple as before, I mean an n tuple decorated with, together with the datum of a composition of the number n. So I put these bars in between the numbers in the n tuple. So n will be n1 plus n2 plus dot dot dot. Let me define some algebraic spaces. So to find the following spaces. First of all, we start with something I'd like to call fcom n1, n2, dot, 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 dot. And I probably have like 10 papers on this subject, and every one of them has a different notation for it. So, yeah.
So it's consistent in some sense, right?
Exactly. I mean, at some point you stop trying to fix everything and just do it as you know. So this is going to be some algebraic stack. Let me just simplify things and call it an algebraic variety for short. It has a map to com n. And you may have seen com n. Com n is the commuting stack of n by n matrices. So a point inside com n is essentially two matrices x and y, n by n matrices, such that y is nilpotent. So about notation in our paper, we call this com n semi-milk, but this is the only version which will appear in this talk, so I'm just going to call this com n, and they commute. So what I've written here for you is an algebraic variety. Matrices are determined by their coefficients. It's a big affine space. The nilpotency condition is algebraic, the commutation condition is algebraic, so it's a big affine space given by the coordinates of x and y, modulo a bunch of equations given by the commutator and the nilpotency. And we take a quotient. We take a quotient by GLN. GLN acts on x and y by conjugations. That's why this is called the commuting stack. Without the quotient here, it's called the commuting variety. With the quotient, it's called the commuting stack. Doesn't matter what a stack is for the purpose of this talk, we won't care. Some kind of geometric space. Now, fcom is going to be a version of this. It's going to also parameterize matrices x and y, but subject to some further conditions. And the conditions are exactly as follows. The matrix X is required to be a block of a triangle. And the blocks are exactly of sizes n1, n2, and so on. On the diagonal of each block, you have the same number, but the numbers can be different between blocks, x prime. Everything below the diagonal is 0. And above the diagonal, we don't have any restrictions. So x is of this form. Y is just a boring old upper triangular matrix, strictly. And we also impose the condition that x commutes with y. And now we take a quotient. We can't take a GLN quotient anymore, because if you have matrices like this and you conjugate them by something in GLN, they are no longer of this form. But we can take a quotient by the Borel of upper triangular matrices. And now there is a map from this stack to this stack, because there is a map from the variety in the brackets to the variety in the brackets, just by essentially taking the closed embedding of matrices of this form into all matrices. So this gives us a map between these two stacks. And the last geometric thing I will need is the fact that there are a bunch of line bundles on this F n called L1 .ln. These are line bundles on the stack F n, and these come from the Borel quotient. So essentially every time you have a variety quotient of Borel, it inherits n line bundles L1 through Ln. It's the same reason why the flag variety, which is G mod B, has n line bundles. The exact same type of line bundles appear here. All right, so I set up quite a lot of geometry. Now let me tell you what I like to do with it. If there are any questions about the notation and stuff? Okay, so let me tell you what a gist of this is. So I defined objects called ED in a topological category. Now let me define some objects called ED in a geometric category. And this will be the comparison we will be presenting. So to this datum, you define the following object called E curly ED, and this will be defined as I push forward of L1 to the D1, Ln to the Dn, and this object is in the derived category of coherent sheaves on this stack com n. Now, found the derived category here, you should put equivariant coherent sheaves, but let me not worry about this thing. So the way this is defined geometrically is the numbers d1 through dn, all of this n tuple of integers, they tell you a line bundle on this F n. The composition tells you the structure of F because it tells you how to break things into block upper triangular, and all of this datum together gives you a space and a line bundle, and then you push forward this line bundle to com n. And com n does not depend on any pattern you chose. So the object depends on the datum d, but the place where this object lives, db com n, is one and the same for everyone. All right, and similarly, similar objects, checked, EP for any convex path P. So, just like over here, the EPs were special cases of the EDs by some kind of combinatorics. Here, curly EPs would be the exact same special cases of the curly EDs. So I'm not going to write down a definition anymore. And here's the gist of this whole thing. This is the conjecture we made with Eugene 2 years ago. So a conjecture, I mean, it's not really a conjecture, it's a hope. But it kind of sounds fancier when you say things as a conjecture. There exists a functor from ter n to dp and this is the realization I was talking about, which sends the object, which sends ED to curly ED for all these. And if you recall, these things generated a trace. So this assignment completely describes what this functor does to objects. It doesn't say anything about what it does to morphisms because we don't have control over morphisms. If I'll have some time at the end of this talk and people are interested, I can say a little bit about morphisms, but we certainly do not understand all morphisms here and all morphisms here, but we have a decent understanding of objects, and this is what how we think this functor should be. So this was our conjecture from 2 years ago, and the paper in which we wrote this, was a very optimistic and upbeat paper saying, we really hope that this functor is very close to being an equivalence. It didn't take us long to figure out that this functor cannot be an equivalence, and now we can make a slightly more refined conjecture which has like an epsilon better chance of being an equivalence. But please take this with
Andrei, is this expected to be fully faithful?
Control morphisms.
No, I mean, I really have no control about that statement. I can't offer anything hard baked goods.
Do you expect at least to be like isomorphism instead of the object?
No, not even that. So this is what we figured out a few months after we made this conjecture and recklessly published it. So I can actually be a little bit more precise about how to fix this conjecture so as at least to make the functor hopefully essentially projective. Lots of adjectives there. But let me tell you what.
What about the case n equal 2? Do you have a good understanding
Um,
of objects on both sides? And
Probably.
and
But I didn't.
is there isomorphism on objects?
To be honest, I never really pursued this because it's like, at least on the geometric side, on this, a derived category of this thing, maybe you can compute stuff for n is equal to 2 by hand by taking doing some intense commutative algebra, but there's no hope of doing it for common. Unless someone comes up with like a technological leap which allows us to understand TB of common, we don't know how to study it. So, I mean, like I said, if I wanted to spend like a lot of time, I probably could work out n is equal to 2 case, but not in a way that would generalize.
N is equal to 1 is good. N is equal to 1 is great.
Yeah, sure. Maybe we could.
You have non-trivial thing there, but you have non-trivial thing. Do you have like one line bundle and like one braid?
Is isomorphism?
Question, what is about K null? What is the graph in the group of TRN?
Of common?
I mean, you have a conjecture of the graph in the group of TRN?
Yes. Oh, not the growth in the group of TRN. I can tell you something about a growth in the group of COM-N, if you'd like. So I'll be a little bit more precise about this, and then people can jump in and complete the picture. So let me write here the slightly more refined conjecture we can make now. So a little bit more refined. It turned out, and this is what we figured a few months after this, that the right thing to hope for is that there is an essentially surjective functor so this should take care of Alexei's question. So it should go from Ter-N idempotent complete, so you need to idempotent complete Ter-N, and you still land in the same place. dB of common. And this should take the objects HP to curly HP for any convex path P. Now I haven't defined the HPs for you. I should just tell you what they are in very, very loose terms. So this is like EP decorated with a specific idempotent. I mean, like some kind of symmetric group isotypic component of ET. A certain idempotent. But we don't know a lot about these HPs. So for example, today over breakfast, we were trying to convince ourselves that HP generate Ter-N idempotent complete, and we did not convince ourselves of that fact. why would this be a natural thing to hope for? Well, the EPs generate this category. We hope that by putting the right idempotence on them, then EP with some idempotence will generate the idempotent completion of this thing. But we don't have this result yet. I mean, it's something that we hope for. However, on this side, curly HP is to curly EP the same way as HP is to EP, some kind of idempotent. You decorate with some idempotent. And one of the few things we know is we know that HP generate the K theory of COM n. So it generates K naught of COM n. And it is a sensible conjecture to make, but we don't know how to prove it. It is a sensible expectation to have that HP also generate the derived category. So, if you do have that the HPs generate the derived category, then the very existence of such a functor implies that it is essentially projective, which would be great. But we still don't have, yeah.
The image is not necessarily triangulated. I mean, the essential image might not be a triangulated subcategory, so...
Yeah, I mean... Yeah, we haven't really thought about that in detail, you're right. I mean, like with Dana's question, I mean, because we have very little control about homomorphisms in this derived category, I don't really know how to prove this thing. I mean, in K theory, you have certain tools which allow you, like some visage proofs, which allow you to take an arbitrary object in K theory and peel off pieces which look like these HPs, but these don't work in the derived category. So, I mean, we have no tools.
The right-hand side, is it idempotent complete? I guess it is.
I don't think you'd have to take idempotent complete on the right-hand side.
Is it? I mean, it's a question. It's a property,
I
right?
think it's automatic.
Yeah, it's automatically
And-
or something.
Okay. And so then you can complete on the left, and you could also join complexes and so on. So, but question, at the risk of sounding like a broken record, should this be a monoidal functor if you take all n?
With respect to the monoidal operation, which takes n prime and goes to n plus n prime, yeah, we certainly believe that. So over yesterday, Paul explained to me that they now know how to make this into a monoidal category, where if you take something in ter n and something in ter n prime, you get something in ter n plus n prime. And this is, like a categorification of what happens for affine Hecke algebras. There is a similar operation here, which goes back to the work of many people in K theory. It was first done by Schiffmann Vasserol, but at the level of the category, it's like a fancier version of them. It's like a natural convolution operation from this thing for n tensor this thing for n prime to this thing for n plus n prime. And these two operations should match under this functor.
Schiffmann and Vasserol only work with a small piece of this derived category. They don't work with...
Well, the construction works for the whole derived category. So they write an extension diagram with push forward and pull back maps. It makes sense for the whole thing.
Is there an affine braid group action on TR1?
Affine braid group action on what?
Not braid, sorry, while group action on TR1.
On TR1?
Yes.
Z, you mean action of Z?
No, affine. I mean, in the finite case, you have a while group action on TR1.
They're off one.
TR of 1.
TR of 1.
Sorry.
I thought I was missing something.
Yeah.
Yes.
TR of 1, yeah, there it is, yeah. So, I mean, I think we can describe the endomorphisms of this object, right? It's one of the few things that we describe.
Andre, does
Yes,
the
yes.
idempotent completion commute with taking trace, or you can start with singular circle bimodules instead?
I don't know the answer to that question. So he's asking if trace of idempotent completion is idempotent completion of the trace.
Oh. I mean, the orbital category is idempotent complete already.
But what is the K null of com n? Can you identify K null of com n as
Yes,
some
yes,
familiar
I
space?
I have that completely. So K naught of comment, we have work which says that this is, K naught of comment is a vector space, really. I mean, it's like a C vector space. There's some kind of equivariance and grading operators Q and T, but let me sweep them under the rug. So this thing is direct sum over all convex paths. conv pass, and here this is C times the class of this current HP. So in K-theory, the HPs actually give you a basis of K-theory as a vector space. And it's actually, I mean, I could even replace C by Z here if I'm feeling particularly ambitious. I mean, this is not 100% true, because it's not Z, but more precisely it's Z of Q plus or minus 1, T plus or minus 1, or whatever. So this is a very strong description of what K0 of common is.
Is it a module over some ring? Is it naturally, what additional structure do you have? Is it a module over some ring?
No, it is. I mean, if you take a direct sum here over all n, then it is an algebra, and this is exactly the decategorified version of what Paul was saying. If you take direct sum over all n, then this thing is an algebra. But the algebra will take you from, when you multiply something in common with something in common prime, you land in common plus n prime. In the same way as when you multiply something in third n with something in third n prime, you get into n plus n prime.
Is it some familiar algebra?
Yeah, it's called the elliptic Hall algebra. That's a good question, because my title is called AHA and EHA. So the AHA is the affine Hall algebra. This algebra is half of the elliptic Hall algebra. So when you take the direct sum over all n, let me draw in a different color so people can tell what's going on. So when you take the direct sum over all n here, this is half of the elliptic Hall algebra that was studied by Budman and Schiffman years ago. So the upshot of this whole thing is that if you believe all of these conjectures, which will take a lot of work to actually prove, I mean a lot of work, and I'm not even sure we have the technology to do this now, so maybe at the QTB in 20 years we will have a proof of this, or we can be a bit more ambitious, but the hope is that you have here a trace of the affine Hecke category summed up over all n should be equivalent, hopefully, to a categorification of the elliptic Hall algebra. So the exact connection, conjecturally, blah, 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 is that, well, the exact connection in my title is that the categorified AHA, let's put here AHA all n, should be, and here we should put the idempotent completion and trace, of the categorification of this idempotent complete should be equivalent to the categorification of half of the elliptic Hall algebra. So this is the hope. So I think this is a good place to stop. Like I said, if anyone is interested in seeing what we can say about morphisms, because everything I've said now was for objects, then ask me. But I think it's a good place to stop. Thank you.
Yeah. So I would this space of Com doesn't have a map to this Steinberg. So
no, there is.
I mean, I done some correspondences, but I'm not sure say that.
No, from FCOM, not COM. I mean,
COM.
Yeah. So I would expect to trace a trace diagram to have some sort of correspondence involving the Steinberg, and this space doesn't seem to fit into the correspondence.
Well, maybe I'm being a bit naive about this, but I mean, I was under the impression that in your talk, the Steinberg was responsible for the constructible realizations.
No. So the coherent realization of the affine Hecke category is coherent shifts on this.
Yes. I mean, that setting, I should have said this, I should have mentioned this. So there are incarnations of this with, you put a Steinberg instead of Comment. There is also an incarnation of this to Hadler and Bensby, where instead of Comment, they put a related stack. I mean, it looks like this, but it's not quite this, but every setting is a bit different. And I'm not exactly sure how to connect all of these settings.
There's also Alexi's inverse setting.
That's true. The matrix factorization is another
diagram in this.
Yeah. No, I think the matrix factorization business is the closest to here, because Alexei's and Lev's framework essentially takes a matrix factorization and can produce an object on this FCOM-N, which is exactly this, and then they push it forward. So, I mean, I guess what it's saying is that one can try to prove these conjectures using their machinery.
So maybe answering your question, you drew the diagram, like GBB, GB, G.
Yeah.
This FCOM is on top.
Yeah, I understand.
But you already lost Steinberg after you kind of went up. So the Steinberg is in the very bottom. So G.
Yeah, but there is no map to the Steinberg in this case.
Oh,
So
yeah.
That's what
Yes,
confusion.
true. That's true.
But you just have your favorite diagram to take G star. And then of course, when you go between two G stars, there is also correspondence.
Okay.
If you start with a much simpler manual category, like category of representations of a finite group, can you say what the trace category is?
I'm sorry.
Just take a much simpler manual category, like category representations of a finite group. Can you say what the trace category is then? Just to get an intuition for this trace category, can you compute it in basic examples like representations of finite group or representations of a half algebra?
The kind of presentation which we gave here is very, very specific for the affine Hecke category. So, I mean, it doesn't really inform computations of traces of categories in general. So, I don't think we can say anything useful about any case other than this affine Hecke in type A. I mean, it's really what matters here are the specific objects Y and T's, these specific Rukier complexes and the specific relations in between them. I can't imagine this holds in any other setting. So, I'm afraid the answer is no.
I mean, you can ask questions like, how does this operation commute? Does it respect the Drinfeld double or the manual category?
The Drinfeld double, that's a very interesting question, but I have no idea how to double these things. I don't even know how to double this thing. So the elliptic hole algebra can be doubled. I mean, the double of the positive half of the elliptic hole algebra is the elliptic hole algebra. But people only know how to do this at the level of K-theory. People know how to double the decategorified version of this. Nobody knows how to double this category. So that's still a very, very open question.
Can I ask the question again? So your Bourbon and Schiffman and there's many co-authors, they studied this area, but they always start with not all, it didn't work with all of the coherent shifts on COM. They only work with the objects which are generated by Nakajima things and line bundles. Somehow they did everything.
It's Bourbon and Schiffman initially he did not study the integral form of this algebra. Instead, he studied the version over this field of rational functions. So this means that you allow yourself to divide by 1 minus q and 1 minus t, which are all operations that we don't want to do with the categorification. But since they only care about K-theory, they can do this operation. And if you work over this ground field instead of over this ring, then the K-theory of this stack is actually the exact same thing as what you mentioned, the K-theory of the substack that is generated by simple Nakajima correspondences. So the upshot is, if you allow yourself to localize, meaning if you allow yourself to divide by denominators, then everything is generated by simple Nakajima correspondences.
Okay,
but you don't want to do that in categorification. You really want to keep in mind that important objects inside here will not be obtainable as products of simple Nakajima correspondences. In particular, this object, curly ED. I mean, if you localize, if you look in K-theory, then yeah, you can break it down into sums of products of Nakajima correspondences, but in general it is not.
Okay, it does not, okay.
I mean, if it did, then essentially everything would be trivial, and it's not. Fortunately.
Okay. So since this functor is conjectured to be essentially surjective, do you, for example, see objects that have nilpotent support along X? Can you, maybe this is a question.
Nilpotent support among X, meaning you want what? You want the locus where all of the X are equal?
Yes. So the image, the support of the objects that you get on COM.
The support of the object on COM is the object you get on COM is supported on the stratum where the a spectrum, the points in the spectrum collide with respect to the cycle type of the braid. Sorry, I was trying to say something and the word just came out jumbled. So the point is that if the braid you start with owns up or not, meaning you don't have these bars in the middle of your tuple, then the object over here will be supported on the smallest stratum where all of the support points coincide.
Yes.
And you know, if you have lots of bars, it's going to live on a big stratum. But the only thing we can say about this object is what stratum it lies on. We don't have any good description.
But it will have, like, the support will have an arbitrary thing onto the end, or
Yeah. Oh, yeah. Sorry. X's are arbitrary. X primes are arbitrary. The only thing that we ask of them is that they coincide with respect to this composition, n1 plus n2 plus dot dot dot.
Oh.
So yeah, I mean, I should really say that x prime dot 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 arbitrary complex numbers.
Regarding the conjecture.
Okay. Can you disprove it? Can you disprove it?
No. No, but just some idea. So chain complexes of type A circle bimodules form a braided two-category. And so one can take factorization homology over the torus. It's a two-category, or infinity two-category. That has a distinguished object, the vacuum. Endomorphisms of that give a monoidal infinity one category, and I think this is TR for all n. So I think this is in range, and then one can hope that this somehow satisfies a universal property that characterizes it with respect to functors out of it.
That would be great. Yeah. Then all you'd have to check is some kind of.
And then you would only need computations on the right hand side.
That would be great. But I mean, his kind of universality statement sounds super hard. I mean, it's your theory, so.
Yeah, that's dreaming. But
I mean, if you can prove this, then I kind of feel like you're more than halfway done in establishing this conjecture. So if you ask me, I mean, of course, this is something understanding objects here was challenging enough, but understanding morphisms and the higher structure is really hard. If you can get such a universality statement, then that describes the left-hand side completely, I think.
One could ask the question at the decategorified level, in which sense that had somehow universal, like this positive half of the Humphrey Thin algebra of the torus. That would maybe give some indication.
No, I don't think we even hope to have anything useful to say about this left-hand side. I mean, you should ask Eugene. He's definitely more competent in the left-hand side. You know, in answer to, I mean, I think it was, I forgot who asked, I apologize, but I'm not videotaped, right? Good. You do.
You are videotaped.
Yeah, okay, because I'm a little bit afraid that just like we found this conjecture to be falsifiable, then maybe this conjecture will be also falsified if it turns out that not everything here can be written in terms of the HP. So once again, the only thing that the only mathematical statement I want to say is that I would be very happy if the curly HPs generate DB. And in that case, we would have a hope that this whole thing would be essentially subjective. So essential subjectivity in my mind is basically I'm asking to prove that these curly HPs is the derived category. So if this turns out to be wrong, then someone is going to have to change this category by something else. So give another description, give another category in here, which would be the right thing where this functor maps. And the right category in which this functor maps is whatever is generated by these curly HPs.
What are HPs? Can you say something?
Yeah, I can say, look, I was hoping everyone would go to lunch.
Start at 12:15 in any case.
Yeah?
Lunch starts at 12:15.
Should we start a talk again from the lofty goal? Okay, so let me show you what that is. What is the idle? Let me draw for you a nicer convex map. origin. This is the point 4, 2. It has a lattice point in the middle over there. That's 2, 1. And then let me actually draw the vector here. So this whole vector is 4, 2. This vector, let's say this vector is, what is the vector? Like 2, 3. Okay, so this is a convex path. The particular EP in this case, let me make a, really hope I don't make a fool of myself. So the vector B, which corresponds to this P, is, you can actually read it off as the powers of y1 and y2. So y1 to the 0, y2 to the 1, y3 to the 0, y4 to the 1, and then here I'm going to need y5, y6 squared. So how do we see this? The number n is the total horizontal length of this path. So this is 2, this is 4, and this here is 6. So in this case, we have a convex path which corresponds to n is equal to 6. So the powers of y are given in a certain sense by these slopes, and the particular p's which you put in, they are prescribed by the fact that you have this segment and this segment. So let's say that you're going to get T1, T2, T3, and then finally you're going to get T5, and that's everything you're getting. So this is the operator. Now, if there were no lattice points, if there are no lattice points on the path except for the vertices, i.e., if the inequality is of the following form: m1 over n1 strictly smaller than m2 over n2, strictly smaller than all of the other ones, then HP is just equal to EP. There's no need for an idempotent. So if all of the mn's are coprime, you don't need an idempotent. But in this example, one of the mn's, so m1 over n1 is 2 over 4, and m2 over n2 is 3 over 2. So what I mean is m1 is 2, n1 is 4, m2 is 3, m2 is 2. And these two are not coprime. Their GCD is 2. And because their GCD is 2, H2, HP in this case is like the alternating part of EP. And in general, the way you get HP is you look at all of the segments. If one segment has k minus 1 lattice points on it, there will be a symmetric group SK action in there. And in that case, HP is going to have to be the alternating part of that symmetric group on EP. And if you have a bunch of segments with lattice points on them, then you're going to have a symmetric group SK times a symmetric group SK prime, and you're going to have to take the alternating parts of all of those. And that's how you define HP.
Other questions? Yeah. Let's thank the speaker again.